So we're the Society for Radiological Protection, and we've got a couple of reasons for doing this today. One is we happen to be in town this week for our annual conference, and for the last few years we've decided that because our charter says that we have to serve the public, that one of the things that we could do is to put on a show for you so that you will have a better understanding of radiation and its uses and its effects, and I hope we've achieved some of that today. Also for the future, we want some of you to think about radiation protection, possibly as a career or just as an interest, and that'll keep us going for future generations as well. So we're going to rely on you to show some enthusiasm there, I hope. We have got a presentation to give you, and I'll shut up and let you enjoy it. I hope you do enjoy it. Thank you.
From beyond our solar system, our world is showered with cosmic radiation. From the rocks which form our world comes the Earth's radiation. And from man's activities comes man-made radiation. Welcome to our radioactive world. Hi guys, hopefully you're all still sitting comfortably in your seats and nobody's jumped too far backwards. Welcome to Eastbourne and welcome to today's SRP show. Now it is a show, it's not a lecture, don't get confused. The purpose of today's show is to get you all to enjoy yourselves and learn something about radioactivity from 3 experts in radiation protection.
Hi guys, my name's Sarah and I work for a company called AMEC Foster Wheeler as a radiological consultant. So my job is to advise people how to work with radiation safely. It's a team effort, so I often get to work with my good friend Steph.
Hello, I'm Dr. Stephanie Bloomer, or as Sarah says, Steph is fine. I work as a radioactive waste advisor on a nuclear power station, so I advise people how they should package their waste and where to send it and things like that. As you can see, it's not always an office-based job. I do get to get out and about as well, but unfortunately they wouldn't let me drive the digger.
I've seen your driving, that's why.
So I'm Dr. Mike Wood. I work at the University of Salford, which is in Manchester. I'm a senior lecturer there. I'm also a radioecologist, so my research life is all about understanding the way in which radionuclides behave in the environment, the way they transfer through the environment, and the way in which wildlife, animals and plants are exposed to radiation. So you've got people that cover human radiation protection through to environmental radiation protection standing in front of you. Now, as I've already said, today it's about a show, it's about a bit of fun. We want you guys to work with us to undertake some live on-stage experiments. We also want to be able to ask you questions as we go through the show today. So you've all got in front of you some card. You should have some yellow card and some green card. These are your voting slips. When you are asked a question, if you think the answer is yes, you hold up the green card. If you think the answer is no, you hold up the yellow card. Does everybody understand how to answer the questions?
That's promising.
Excellent. Most people are holding up green. That's very, very promising. When you hold them up, can you make sure you hold them high so that we can all see how you're voting? So, okay, first question then for today. Are you being exposed to radiation right now? Yes or no? Green is yes, yellow is no. Oh, I'm impressed. We've got a sea of greens. Fabulous. That's correct. We are all being exposed to radiation right now. If you have a look at some of these pictures up here, it gives you an indication of the kind of sources we're talking about. So we get radiation that's coming from the solar system, cosmic radiation. We have terrestrial radiation from the Earth underneath your feet. We've got natural radionuclides in the building materials that surround you. Radioactivity is in the food that you eat. It's in your bodies. You are all walking sources of radioactivity. It's everywhere. But today we're going to talk about the radiation that we encounter in our daily lives and also think about how we ensure that people are protected from radiation. Okay? So when we think about radiation, we're talking about radioactivity. What are we actually talking about? We're talking about emissions, radioactive emissions. And we have three principal types. We have alpha particles, which are these large radioactive particles, pack a big punch. It's basically a helium nucleus. We have beta particles, so for example, electrons. And we also have gamma photons. And gamma photons are going to be the source of quite a lot of the discussion that we'll have during the course of today. So we're talking about radioactive emissions. If we think about activity, what do we mean by activity? Well, when we use a unit of measurement of activity, that unit is the becquerel, and that means 1 radioactive disintegration per second. So if you've got 1 radioactive disintegration taking place in a second, you have 1 becquerel. We can't see radioactive disintegrations happening. We can use detectors, radiation detectors, to help us determine the rate at which these radioactive disintegrations are taking place. And you're going to have the first live experiment now, in which we look at some everyday household objects and see if we can determine the level of radioactivity within those objects.
Okay, can we have our lovely volunteers on stage, please? We'll give them all a round of applause. Thanks, guys. Can we have 2 on this table, 2 on this table, and 2 on this table? Thank you. Can I just get your names, guys, and what school you're from?
I'm Jess, I'm from Seaford Head.
I'm Oscar and I'm from Seaford Head.
I'm Jack and I'm from Seaford Head.
If you've got any supporters in the audience, they can cheer for you.
I'm Harriet and I'm from St Dunstan's. I'm Rebecca from St Dunstan's.
Right, guys, since we're going to be doing a science experiment, can you all get kitted out in your protective equipment here? We've got the lab coats and the gloves and the glasses for you. Just pop those on while I describe what we're going to do. So we've seen that activity can be measured with the becquerel, and we're going to look at some everyday items and see if you can figure out whether they contain radiation or not. So on the table in front of us, we've got a rock, a glass bowl, some Brazil nuts, a watch, a smoke detector, and some salt. So what I want you guys to do is to think about the items you've got on your table, and in your teams, put them in the order of which you think is the most active to the least active, right? So we've got the highest activity on this side and the lowest activity on this side. So if you can just line them up. And if you guys want to give them a hand, shout out to your schoolmates which order you think they're going to be in. They've got a minute to do that, okay? We all ready? We all kitted out? We all safe? Okay, let's start the timer. Go, guys.
Right,
So
you've got a minute to do this. So you've got to
Least
discuss
radioactive on
between
this
the
end of the table.
So we've got
And
the
most
low
radioactive
radiation
up
here
that
and the
end of the
highest
table.
there.
Based on not very
Do
much.
you
Does anyone want to
this
give
is
them any
high
hints?
or
Do you guys
low?
know in the
Yeah.
audience? That's just a rock, right? Brazil nuts. What are you thinking? You're not thinking
this is
Brazil is
low.
radioactive, okay?
Low, high.
Call for Brazil nuts. They are. Call for help from your friends. High-ish. Right. Okay.
So you think the salt's the highest radioactivity?
Right, you've got to
you
get
done?
so.
You've got 18 seconds. It's your
15
final
seconds.
answer. Yeah. Okay, 8, 7,
Come on,
6,
you run out of time,
5, 4, 3, 2, 1. Stop.
There you go.
Okay, guys, what have you got? Is that your final answer? So you think the lowest activity is the glass bowl, the Brazil nuts, we've got some no's in the audience, the watch, the salt, the smoke detector, and then the rock. Okay, you guys have got the glass, Brazil nuts, the rock, the salt, the smoke detector, and then the watch is the most active. And you guys think it's going to be the bowl, the rock, the watch, the salt, the Brazil nut, and then the smoke detector. So let's see what the correct order is, please. Okay, so Brazil nuts are actually the lowest. Then the low salt, the Vaseline glass, the watch, the smoke detector, and then the rocks. So which table do we think has won? Mike, what do you reckon? Who's our winner?
Well, we're right up here, but we're looking a bit dodgy for the rest. Not quite right there, are we? Everybody seems to have gone glass as low, which is a bit of a surprise. But let's work on where we think the highest activity is.
So these
and
guys
this
have
is
got
definitely working right. So I think this
it's
table
gonna
over
be
there
these
are the
guys. So
winners.
thank you very much, guys. You're the winners. Okay, do you want to go off that one, thanks? Okay, so big round of applause for our volunteers. Thank you. You go after that side for us.
Thank you very much, guys. It's all right, you can take them off like that. Yeah, that's fine.
And I'll put these in the correct order now. So we said Brazil nuts were the lowest, the glass bowl. Oh, salt, sorry. Thank you. The salt, the glass bowl, the watch, the smoke detector, and then the rock. So I have my glamorous assistant here. So you can't see radiation. We have to use an instrument in order to help us to look at what radiation is. So the Brazil nuts were first. Each click from the instrument is for a disintegration. So that's a count of how radioactive this substance might be. So the Brazil nuts, you can hear a few clicks, but not very many. Now, Brazil nuts are radioactive because of radium in the soil. So it's in the soil naturally, and the roots of the Brazil nut tree uptake the radium and store it in the nuts. So that's why they're slightly radioactive. If we move now onto the salt, this is actually low salt. So it's a health alternative to regular salt. So it actually contains potassium chloride rather than the regular sodium chloride. Okay, and potassium has 1% of potassium-40 in it, which is naturally radioactive. So anything that contains potassium will therefore be radioactive slightly. Now this bowl is not just a regular bowl, it's made from Vaseline glass. Now Vaseline glass, we just listen there for a little while, the increased amount of clicks. Vaseline glass contains uranium, and that gives it its characteristic green colour. And so uranium is radioactive, and that's why we get a reading off of that. Now, if we move on to the watch, Steph, please. That was actually a bit of a trick. The watches that were on your table were not radioactive, but radioactive paint was used quite extensively on watches to make the dials glow in the dark. Now, if prior to 1960, when we used radium paint, that's the kind of reading you'd get from it. But because of the health hazards associated with it, we stopped using radium on the dial. So those ones are not radioactive anymore. Now, if we move on to the smoke detector, everyone was quite right and put them up this end, didn't they? Now, if you can find the source for us, Steph, quite a lot of clicks there. That's because the smoke detector contains americium-241. Now, that ejects an alpha particle, which is a charged particle, which, when it interacts with the smoke, it charges the smoke particles, completes the circuit, and that's when the alarm will sound. And then finally, we had the rock, which confused a few people on the tables. Now, this rock is actually from Cornwall, because there are... there we go. It's quite loud. So there is uranium and thorium in the ground naturally, in the rocks and the soils, but in certain places, they have much higher concentrations than usual. So in Cornwall, that's a good example. They have much higher levels of uranium and thorium in the rocks and soil. So that's why that one was particularly high. But we can compare that to a rock from outside. I picked this up from the beach yesterday, from Eastbourne. And because it's a different type, you get kind of a regular amount of clicks. Okay. Now, if we move on to the next question, thinking about this rock, will this rock always have the same amount of radioactivity in it? What do you think? Green for yes and yellow for no. Is it always going to say the same activity? What do you reckon? So we've got quite a lot of yellows there. So Steph, can you let them know? Were they right?
Let's see. No. The answer is no. Of course, it's the reason they're emitting radiation is because they're trying to reach a stable state. So the rocks are going to very gradually get less and less radioactive. And we're going to have a little look at radioactive decay now. So what we're going to do is we're going to try and simulate the process of radioactive decay in the statistical pattern that it follows. I've got another glamorous assistant here bringing on an important part of equipment here. You may have heard of cooling ponds on nuclear reactor sites. Thank you, Radioactive Man. It's a good job you've got the muscles to carry our paddling pool on for us there. Right, thank you. So we're going to take a look at some live statistics now. Are we going to select another 2 volunteers from the audience, Chris? If you could, please. Oops. Thank you. Right, so who have we got here?
Harvey
from Seaford Head.
Okay, and
Jack from Seaford Head.
Jack from Seaford Head. Again! You had so much fun the first experiment. Do you want to grab that again, Mike? And then I think Mike and Sarah are going to help us out as well here. So if one of you gets kind of here either side of the paddling pool and grab
Help me over this side.
grab your
with this
bucket. Yeah. So yeah, we just get about here. So what we've got here is 2 buckets full of radioactive particles that are getting ready to decay. So we're going to throw them into the paddling pool in a sec. If they land trefoil upwards, then that will represent a particle that's remained active. It's not decayed yet. If they land plain side upwards, that's going to have decayed, and we're going to remove that from the experiment. So, on 3, tip your buckets.
Dr. Steph, can I just
into
check?
the, yes?
Would you like assistance with this demonstration?
Sure, yeah.
I
Yep.
think that he could be quite good at recording the information.
Yep, yeah. Are you ready for some data input, Radioactive Man? Is this part of your normal role on the as a superhero? Maybe? Yeah? Okay.
Excellent.
Great. Radioactive Man will be recording how many particles decay each time.
And how many are we starting with?
And we started with 84 in
84.
total.
So
84 discs. I've
Do we need him to
pre-counted
put that into a
these.
spreadsheet?
Yep. Have we got 84 ready? Yep. Okay. So, on 3, chuck your discs. Ready? 1, 2, 3. In. Chuck! Yes. Oh, you've missed some. Put them back in the bucket. Right, okay. So, ones that have not decayed into...
You help me pick
Back
out
into your buckets.
the ones that are decayed.
So, pick up the back ones.
So anything that's
Pop them in your
face down. Just the face down ones.
So can we predict
into
how
that.
many will
So-
have decayed, do you reckon?
Oh yes, how many, anybody got any ideas how many particles we think will have decayed this time round in the audience? Do you want to shout out? We had 84 originally. Duncan, you're not allowed to answer, no. Anybody? No? 47? 100? No, we're not going to have 100 have decayed. That's silly. Okay, are we there?
We're there.
Right, let's get rid of these decayed particles. So now we're going to count how many we've got left.
So could you guys hold the buckets for us, please?
Okay, so I will be doing the counting. Trained
Concentrate.
counter, professional counter. If you guys could help me out with counting, that would be great. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41.
Not bad.
Good job I practiced that counting because I wasn't getting much help from the audience then. 41. Thank you, Radioactive Man.
They're
Okay.
impressed that you could count to 41.
I know. We have been practicing this morning, as I said. Right, okay. We're going to have another radioactive decay now. So on 3, chuck your buckets into the pool again. Ready? 1, 2, 3. Okay. Pop the
Very
buckets back
stylish.
down.
So blank ones again.
Blank ones, if you help the guys, blank ones into the buckets. So, last time we had 41 out of our 84 remaining. Any ideas how many this time? Approximately a half. I think was. Okay, how many have we got? We're going to count
So
again.
can you guys hold buckets again for us?
This is a smaller number, but I can still do with help counting, I guess. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Woo. 21. Did we have a winner?
Excellent.
So we can see some live statistics happening. We've got some live graph action now on stage. Okay. Again, next disintegration, please. 1, 2, 3. Shut. Okay, blank ones out. Right, how many do you think we're going to have left this time? The awesome math skills. Okay. Have we got all the blank ones out?
Right, you guys, buckets are ready?
Okay, ready? 1, 2, 3, 4, 5, 6, 7. 7. 7, Sean.
Oh, explain that, Steph.
Well, as we mentioned, it is a statistical process. Each time a single atom decays, it's not possible to predict whether one atom is going to decay or not. You have to group all of the atoms together, and you look for general patterns rather than a single atom at a time. So chuck them back in again. Okay, blank ones out. We're getting there now. Right, off with the blank ones.
So,
We're going to chuck them back in your buckets.
1, 2.
2. 2.
Down to 2.
Right,
Okay.
back in again. Oh, exciting stuff. One blank one. Give the blank one to Jess. Do you want to have the last one?
Are you going to count?
1.
There we are. There we go.
Back in the pool.
And it's decayed.
Finished. Stable.
There we go.
Stable, no longer radioactive material.
Exactly.
It's all
Thank you
decayed
very much,
away.
guys.
Thank you.
And you can see a lovely
hang there for a
exponential decay has appeared before your very eyes. Thank you very much for your help.
So, big round of applause. Thank you. I'll sort that while you sort the cooling pond.
Radioactive man, I think I will need you to remove my paddling pool again. I can't possibly... Yeah. Thank you. So, as we said, decay is a statistical process, and one of the terms that we use to describe decay is half-life, which describes the amount of time it will take for half of the material to decay away. Each different radioisotope will have a different half-life, and it'll take a different amount of time to decay and become stable. And the constant that we use to describe that is called the decay constant. And of course, we have applications for these radioisotopes as well. For example, one instance where you would want some material that decays away quite quickly would be in medical procedures, where you might be looking at what's going on inside the body, but we want to minimize the amount of time that the patients are exposed to radiation, minimize their exposure to radiation. So we use isotopes that have quite short half-lives so that they've gone quite quickly. So I think we've got another question now. So do you think the medical staff administering these treatments would be exposed to radiation if you use your cards again? A few greens, a few yellows.
Come
Will you
on,
hold them
commit.
up-
I can
hold
see
them up
there's a
nice
few
and
people that are
high?
holding their cards down like this.
Yeah.
Come on, decide which one's going to go up.
Put those cards up in the air. Right, okay. So we've got a reasonably mixed bag this time. And the answer is yes, they are being exposed to a certain degree of radiation during their jobs. But we've got radiation protection professionals like ourselves who look into how much radiation they're getting and try and minimize it and make sure that levels are safe for them to work with. And there are a number of different ways that we can minimize the amount of radiation that people are exposed to. And that's what Mike's going to look at now.
Okay, thank you. So, yes, as we've said, people are exposed to radiation throughout their daily lives from the radioactive world that surrounds them. They're exposed to radioactivity in particular jobs that they do. And when we think about how we protect people from radiation, we need to think about the nature of radioactivity as a contaminant versus something like chemicals, which many people are much more familiar with. So what's one of the fundamental differences between the two? Well, to illustrate it, I'd like to start by getting you all to look at this bottle. Now, I assure you, it is a bottle of water. But for now, I'd like you to pretend that this is a bottle of sulfuric acid. I'm going to put the bottle, sealed, over there. I'm going to come over here. If I stand here with that sealed bottle of sulfuric acid over there, am I being exposed to the sulfuric acid now? Yes or no? Great. Most people are holding up the yellow for no. That's correct. I'm not being exposed to it. Fundamental difference between chemical and radioactive contaminants is that for a chemical contaminant, you have to be in physical contact to be exposed. Now, that physical contact can be that you ingest it. Physical contact can be that you touch it. Physical contact could be through inhalation of vapors. In any of those instances, there is direct physical contact, you can get exposure. Now, this sealed bottle contains a mixture of gamma-emitting radioactive isotopes. I shall stand over here. Am I being exposed to the radiation within that bottle? Yes or no? Excellent. Yes, I am. The gamma photons coming out of this travel through air quite happily, and I am being exposed to the radiation that's coming from that. That's just me talking about things. That's not a particularly interesting and exciting on-stage live experiment to do, is it? Let's have a look at the way in which gamma photons move, and let's think about the things that we can do to reduce exposure to gamma photons. Now, I'd like one volunteer from the audience to come up and join me on stage to help me with this experiment. Excellent, thank you very much. Come on up. Welcome. So, what's your name?
Isla.
Isla, and where are you from? Which school?
St. Dunstan's.
St. Johnston's?
Dunstan's.
Dunstan's. Right. And have you been involved with a live stage experiment before?
No.
Are you apprehensive or are you excited?
Bit of both.
If I say that I'm going to get you to control an unstable radioactive nucleus, which is releasing gamma photons, would you be comfortable with this?
Absolutely.
Hey, this is confidence. I'm liking this. Well done. Right. Could somebody please pass me an unstable radioactive nucleus? Here we go. One unstable radioactive nucleus. Have you seen one of these before?
Yeah.
Yes, you have.
Yeah, similar to it.
Yeah, so what is it then?
It's a gun.
A gun.
A Nerf gun.
Right, okay. So it's not an unstable radioactive nucleus?
Well, no.
You're on stage, work with me.
Yes, it is.
Excellent, yes it is. It's an unstable radioactive nucleus. And it fires gamma photons, doesn't it, Isla?
Yeah.
Yay, there we go. So it fires gamma photons. So what we're going to do is we're going to use the Nerf gun to represent an unstable radioactive nucleus, which is going to release gamma photons which fly through the air. We need a target, something that can absorb these gamma photons as they fly through the air. We need some willing idiot. Have we seen somebody on stage already who fits that bill? Radioactive man? Yay, thank you. Radioactive man, welcome to the stage. Please, come on. Now then, what we're going to do, Isla, is we're going to experiment with our concepts of time, distance, and shielding. Radioactive man, tough as he is still putting on his safety goggles because we're a safe experimental setup. So, Dr. Steph, can you open up a spreadsheet, please, for me? Thank you. Now, Isla, could I ask you to come and stand over here, please? In a second, I'm going to ask you to unleash your gamma photons at radioactive man. This area here, the black area, is where those gamma photons are going to be received. That's where you're aiming for, yeah? Oh, go on.
You said they were a very safe experimental group. What did you forget? One thing you forgot.
Would you like some safety goggles? Oh, she would. Has somebody got some safety goggles, please?
There were.
Thank you. Now you look ready to do real science. This is good. This is what I do in the lab all the time at the University of Salford. I sit there just unleashing gamma photons at will. So, it takes about 7 seconds to fire all of those gamma photons. I would like you now to make sure you're powered up and fire those gamma photons at Radioactive Man. Off you go. Hey, look at that, everybody! Let's see how many gamma photons were absorbed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 gamma photons, all absorbed by Radioactive Man. Thank you. So we'll get rid of that unstable nucleus, and we'll welcome a new one onto the stage. Now this time, rather than 7 seconds, you're going to have 3 seconds to do this. The idea is we're reducing the duration of the exposure and seeing what that happens in terms of the number of gamma photons that are absorbed. So, everybody will count together down from 3 when I say go. So we'll go, 3, 2, 1. When we hit 1, I'll yell stop, and you stop firing at that point. Okay? Ready, set, go. 3, 2, 1, stop. Now let's see what's happened to the level of exposure. How many gamma photons have been absorbed? 1, 2, 3, 4, 5, 6, 7, 8, 9 gamma photons have now been absorbed by Radioactive Man. So we reduce the duration of exposure, we reduce the number of gamma photons that are absorbed. So that's experimenting with time. What else have we got on our spreadsheet? Let's have a think about distance. Well, the distance at the minute is about 3.5 meters. So we've already figured out that we get 20 photon hits at 3.5 meters. Now what I'd like to do is I'd like to move Radioactive Man to 7 meters distance. And with our next unstable nucleus, you get to run the experiment once again. So, in your own time, off you go. Now remember, it's the ones on the black that count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 gamma photons hit at the increased distance. So, by increasing the distance, we have reduced the exposure to gamma photons. So we've looked at time, we've looked at distance. There's one other thing that I mentioned, and that is shielding. So now we're going to offer Radioactive Man the opportunity to use some shielding to help protect him. So if we can have the shields come on stage. We've got 2 shields to test out today. Now, the keen-eyed amongst you will notice that there are a couple of differences between these shields. We have a green shield and a red shield, but you will also hopefully see that there is a different amount of shielding provided by each one. So, does the red shield have less shielding than the green shield? Answers, please. Mostly greens. Yes, you're right. This has less shielding. So what we'll do is we'll give less shielding to Radioactive Man. Here you go, Radioactive Man. And Isla, I would like you to pass me this. You will get a fully loaded, unstable nucleus. And now, aiming once again at the black target area, with me out of the way so I don't get hit, I would like you to release the gamma photons at Radioactive Man. Off you go. Way, look at that, guys. Well done, Isla. So how many hits have we got now? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hits with that red shielding. Okay? So what happens if we give Radioactive Man some additional shielding? Here we have the green shield that we can try. Again, I will get you a fresh, unstable nucleus. Allow me to get out of the way. Isla, please hit him. Off you go. Way. Excellent. Well done, Isla. Wow. 1, 2, 3. 3 hits on Radioactive Man. So you can see that we've gone from 9 gamma photons being absorbed by Radioactive Man down to 3 as we've increased the amount of shielding. So we've shown that if you reduce the duration of exposure, then you reduce the number of gamma photons that hit. If you increase the distance between the source and the target, you reduce the number of gamma photons that hit. And if you increase the amount of shielding, you reduce the number of gamma photons that hit. Now, in radiation protection, we don't do these things in isolation. Often these things work in combination. So we're going to give you one more go at shooting Radioactive Man. This time, we're going to put Radioactive Man at 7 meters with his shield. We're going to get you a fresh, unstable nucleus. And with that unstable nucleus, you are going to have 3 seconds with which to hit the black area on Radioactive Man. Again, I'd like you all to count with me. Are you ready? On your marks, get set, go. 3, 2, 1, stop! He is protected. Thank you. A bit of fun on stage, but you can see that it demonstrates an important principle that when you start to combine these different ideas of time, distance, and shielding, you can reduce radiation exposure to very low levels. Isla, you've been fantastic at demonstrating this for us. Thank you very much. And thanks to Radioactive Man.
So we're just going to ask you a few more questions now. If you remember back to that rock that I had before from Cornwall, is the rock from Cornwall radioactive because of something that humans have done? What do you think? Green for yes, yellow for no. I reckon everybody thinks no. So let's see the answer. That's correct, you were right. The answer is no, and that's because radioactivity has existed since the Earth was formed. It is decreasing slowly through radioactive decay, though. Okay. Next question.
If you move away from a radioactive material, does your exposure increase? Green is yes, yellow is no. Excellent, that experiment worked well. You've all got that right. Marvelous, well done. No, it doesn't. You move away, you reduce the exposure. We've got 4 take-home messages that we want to run through with you. Yeah. So, first of all, we discussed radioactive materials. and we said that radioactive material is all around us. This show was entitled Our Radioactive World. We've hopefully demonstrated to you in the discussions about the radioactivity in your bodies, in your food, in the building materials around you, coming from the solar system, coming from the Earth's radiation, that you are continuously exposed to radiation, but not at harmful levels. Next.
Okay, you also need to remember that you couldn't actually see the radiation on the objects that we had on the table. You couldn't see the radiation coming off it. That's why we had to use the instrument to detect it.
Radioactive decay, as we said, is a statistical process, and you can estimate how much is going to decay using equations and predict what's going to happen, which obviously has very useful applications.
And within radiation protection, as you've seen, we can use the principles of time, distance, and shielding to help reduce radiation exposure and ensure that people can work safely with radioactive materials. So they're the key take-home messages for you from today. So you've hopefully learned something, but hopefully you've also enjoyed the fact that you've been able to play around with some live on-stage experiments and get involved. I'd like to thank all of you for being a great audience. Without this sort of support from you guys, we couldn't do these kind of experiments on stage anyway. So thank you to all of you. I'd particularly like to thank the volunteers that came up to assist us on stage. You did a storming job. Well done. And Isla, if you ever decide to become a sharpshooter, I think people need to run. You were very good. Well done. To put on this show today, we've had sponsorship from a number of sponsors who've enabled us to get you here and put on, hopefully, an enjoyable day for all of you. So thank you to them. And I'd like to say a big thank you to all of those volunteers who've been working behind the scenes to help provide us with things on stage. And, of course, our hero of the day, Radioactive Man.